like me to demonstrate or to talk about, please make suggestions. But I guess I did sort of put together a short list of things that I thought might be both partially interesting, but also things that I use most in my work, I guess. And so I think maybe I'll lead off with a couple of web resources. I think that could be very useful for people. And so I guess first of all, for people who are interested in exploring the astronomical literature, the various published papers, there's two sites that I use constantly. And so the first of these is the ADS, the Astrophysics Data System, which you can find it by searching NASA ADS. And this is a search engine for physics and astrophysics papers, primarily for astrophysics and astronomy. And essentially any paper published within, certainly I think within the last 10 or 20 years, you will find on here. And you can find, I think, the vast majority of papers in the main journals going back maybe 100 years, I think, in some cases. And so it basically operates as a standard search engine with some ability to sort of narrow down things. So for example, if I want to search for the papers that I was the first author for, I just do so in sort of the typical way. And this turns out, a list of papers in which I'm the first author, as well as things like catalog data as well, which I'll also talk about a little bit later on, hopefully. And so I can basically search through. Actually, there is another Van Eck. There's a Sophie Van Eck in Belgium who's an astronomer, and so her papers come up as well unless I refine the search with my first initial. That narrows it down quite a bit, actually. So this is a great tool for if you know a particular paper that's a particular author, particular paper, or something. But you can also, in principle, you can search just on keywords. And so if you're interested in the most recent pulsar research, you get 39,000 papers sorted by most recent. You can narrow down by keywords. For example, if you're interested in a pulsar catalog, that narrows it down. Things like that. And so if you're going in a bit blind, it can be a bit difficult to find the paper that's most relevant for your needs. But it will be on here. It's just a matter of finding the right combination of search terms, I guess, that gets you there. And in conjunction with that, and this I think will be particularly useful for those who are not associated with universities, and that is the archive. And so for all of these papers, in principle, you can get them from the publishing journal. This one might be open access, actually. So some journals have all of their papers just publicly available. This one, it looks like this one is not actually public at the moment. This is to access the article, you either go through sort of if you have a library access through a library that has access to all of these journals, then you can access it through that system. There's usually a login system that'll sort of authenticate that you are allowed to access that library's resources, or you typically have to pay for them, which is not a reasonable outcome, generally not a reasonable thing to do. And so if you find a paper like this that you think looks really interesting, but if you don't have library access, then you generally, in astronomy, you have two options. The first option is you could contact the authors, and most paper authors will be happy to just send you a PDF. But the easier thing to do these days is there's a website called the Archive, which is a repository for, it's technically not a repository for papers, it's a repository for preprints, which are versions of papers that have not yet officially been released. But these days, people just use it as a repository of their papers, and it is an open archive, and you can just get the PDF. And so, in principle, you can, in addition to the ADS, you can just search the archive for relevant papers. There's an astrophysics section here. I think it doesn't have a particularly strong search engine functionality compared to the ADS, and everything that is on the archive will be in the ADS search. So I recommend, if you're searching, I would recommend ADS. But I mean, if you're just interested in exploring, you can do fun things like, for example, every day they put out a list of new papers that have been added to the archive, and so something that I do is as a daily routine actually is I get this emailed to me every day, and I will quickly scan through this every day to see if there's anything relevant to my particular research specialization or anything that looks interesting. And so I usually spend 5 minutes first thing in the morning just sort of scanning through. I think there was some interesting papers today or yesterday or the day before, so I'm not sure if they'll be on this page. Who was the authors on that? Was that okay? That would have been yesterday's maybe, but probably recent. So this would be the last five days or so, I think. Oh, it's not on here. Okay, I must be misremembering. But anyways, so this is the easiest way to access the most recent papers as well as papers that are not publicly available. And so yeah, so you can just pull up a PDF and you have access to what is technically not the official version of a paper, but it is generally indistinguishable from the official version. It'll be formatted slightly different, but it will have the same contents, except maybe a few spelling errors or typos that the journal will catch at the latest stages of publication. And so the archive version is sort of the definitive version defined by the authors, whereas the published version is the definitive version by the journal after proofing and typesetting and stuff. And so yeah, basically anytime that you want to, or at least in my case, anytime I want to go and find something in the published literature, this is where I go. This is my cycle. Is go to the ADS, try and come up with the best search I can, find the most relevant. Or in some cases, there's some neat tools like if you know a paper that is relevant to the question, you can see all of the papers that it references. And so this is all of the papers I cited in my last paper, and so I can say, okay, which of these is relevant to a particular question that I want to address. And so say I'm interested in something relevant to this paper by Sam George, for example. I can then go click on that, go to that paper, and then immediately pull up the archive PDF of that to find every detail. And so this is I think a very streamlined and effective way of scanning through the literature for particular questions. Does not always make it easy. I spent a fair chunk of last week trying to dig down some citations. And I did eventually manage to find it, but it did take me a couple of hours, I'll confess. But I was trying to find something from the 1970s, and I did eventually succeed. All right, let's see. What's next on my list? Or is there any questions? Any questions that you can interrupt by voice, or I am trying to keep an eye on the whiteboard channel as well. So the next one, I think some of you may have seen this before, is there's a series of websites run by something called the CDS. CDS is, let me find it. What does CDS stand for? Center. What does CDS stand for again? Something Strasbourg. Center de Astronomy de Strasbourg. So this is essentially a series of astronomical web resources run in France, provided for the world, and it can be very useful for various purposes. So the first one I'll show you is Simbad, and this is essentially a super catalog of astronomical objects. And so it's essentially a collection of data from a number of different major astronomical catalogs, and then it's pulled out a bunch of basic reference data. And so there's different ways you can search by coordinates or try and narrow it down, or if your object of interest has a particular name, like say I'm interested in the star EWCAM. This is a variable star, our Lyrae type. And so you can immediately pull out its coordinates in the different astronomical coordinate systems, brightnesses, and so I can tell this is 9.5 magnitude visual band. things like that. And so for someone who has enough of an astronomy background to sort of be able to read a bunch of this basic data, it's immediately a very quick and easy reference. I know how bright this star is in the optical, I know where it is in the sky, I know its type, and I have the ability to search it up in related catalogs, like, for example, the Gaia catalog. If I want to get information about what the Gaia satellite observed on this star, things like that. Distance measurements, it sort of has an archive of distance measurements and stuff like that. And so it's basically a very quick and easy resource for basic information about various kinds of objects. They have galaxies. Well, I can pull up my favorite NGC galaxy. So yeah, very very nice, highly inclined galaxy. Here gives you the visual, sort of the optical view on the panel there, and then all the relevant data there as well. And so if I'm curious, for example, how far away is this galaxy, I can then immediately have all of the distance measurements that have been archived by Simbad here. And so yeah, 10 different distance measurements to this galaxy taken between 2007 and 2019. And so that gives me a sense of maybe what the error bars are, or the uncertainty, between different kinds of distance measurements. And so a lot of very easy, quick information to be had there. Second service of CDS that I use quite a bit is Vizier, which is a catalog repository. And so whereas Simbad is essentially a super catalog where it's just taken some of the basic information from some of the biggest catalogs, Vizier is a collection of 21,000 individual astronomical catalogs that have been published by different people. And so essentially any information that you think has been cataloged about radio sources should exist on here somewhere. And so yeah, here's a catalog I did technically this year. It came out. And so you can sort of search for sources, particularly if it's a big catalog. You can search based on location or on certain properties that have been measured in the catalog. Or in this case, I can just say, give me the first 50 or 100 rows. And so this is an astronomical catalog of a series of measurements. In this case, this is work I did on measuring the polarization of radio sources. And so I have the position of every source. I have some polarization properties here and measurements of its brightness in different units. Things like that. And I am seeing mistakes in this. That's not good. I'll have to fix that. But yeah, and so this is essentially an easy resource if you know that someone has published some measurements and you just want to get the numbers quickly. This can be the easiest way to get them because they're all stored in essentially a master database in one place, and so it saves you the effort of having to go hunting through the literature or through the internet to try and find some published data essentially. And so catalog data, I guess, not image data, but so yeah, not going to be useful for everyone, but it is a really fantastic resource for anyone who is dealing with with this kind of data essentially.
Cameron, can you go into more detail, like what goes on, like behind the scenes while you are making this catalog or any catalog?
Yeah, that's a big question, I guess. I can actually pull up this paper, I guess, and maybe I can show you a little bit. Is essentially catalogs are the output of big observing projects where you say, okay, I want to go out and observe a population of some kind of astronomical object, and I want to measure some properties of each of these objects. Here's the PDF. And so you go out, you measure something for a whole series of objects, and then you want to report the results in kind of an organized way. And so yeah, this is a paper I did reporting something called a rotation measure, which is a polarization property in the radio regime. And I'll skip over. I mean, most of this is not relevant information in a broad sense, but essentially, I had like in my case, I developed an entire software pipeline is a bit grandiose, but basically an entire set of procedures that I had to code up to take some input data, which was radio observations I was given, and basically extract all of the radio sources and then analyze them following a series of steps, which went on. It took quite a while to actually get all of this put together. So there's a whole series of steps in which we analyze the data and assess. There was quality assessments done to say is this a good measurement? Does it appear to be a valid measurement? Things like that. And then in the end, we ended up in this case, I think, with some 2,000 odd measurements of these rotation measures of different radio sources, essentially. And so we ended up with all of this data, and in the end result, it's like, okay, we have for each source we have some measurements of its location and all of the other parameters that essentially came out of our measuring algorithms that I wrote. And so rotation measures and errors. I'm not going to rotate this, but that's essentially the basic procedures. You have some data, you process it, you analyze it, and you get some series of measurements. And then the rest of this paper is essentially just analysis. Does that kind of answer the question?
Yeah, you did. Can we
Okay,
look at the
sounds
code?
good.
Like, is this paper open source right now?
So this paper is as I demonstrated with the ADS, the official published version is not public, but the archive version is public.
Okay, so
The
can you
paper
like
itself
send
does not include. Sorry.
can you send the paper in whiteboard? Like if it's openly available.
Yeah, I can pull up. Let's see how quickly I can find it here on the archive. Author. Oops. Help if I spell my name properly, wouldn't it? Live demos. So this is all the papers that Simbad has been on recently. So let me see. Wow, I can simplify this. So beginning of 2021, right? This is not a sorted list? Oh no, here it is. Yeah, this is the one. So yeah, I can link this on whiteboard. There we go.
Yeah, thank you for that. And also,
So
like,
yeah,
how
so
you
that's my
come
most
up with?
recent publish.
Congrats on that as well.
Thank
So
you.
also, like, how you come up with those pipelines? Like you talked about the software pipeline and the statistical methods where you test the quality of the data. Like, how does one come up with that?
I mean, in a broad sense, it's a little bit, some combination of trial and error and knowing what your end goal is, in the sense that you start with some data, which you would get from an observatory but typically, from an observatory or maybe some telescope that you have yourself. You start with some data, and you generally have some end goal in the sense that I want to measure X. And so, the question then becomes is what are all of, how do I get the data into, the required state? And so first you have to answer questions relating to calibration, which is, all the questions of, okay, how do I make sure that like things like the brightness are calibrated and whatever other aspects of the particular data are well behaved. And so usually this is not something that you come up with from scratch, in the sense that other people have done similar things with similar data sets before, and so you can use algorithms that have been developed by other people in the past, or follow similar methodology to arrive at some data that, as near as you can tell, is trustworthy and calibrated. And so that part is often done by using known sources. Calibration is done using a source with known properties. So, like particularly in the radio, we have a known set of calibrator sources which have been very carefully measured and monitored over the years, such that we know how bright they are, we know where they are, some of their other properties, their spectrum. And so, any radio observation, for example, will include one or more of those calibrator sources, and you use those to essentially set the data or calibrate the data in its various aspects. It's hard to talk about in a very general way because it is very specific to different kinds of data sets as to what the procedure ends up being. Actually, yeah, just for the fun of it, I should have another figure here for a pipeline that I'm developing for new data sets in the future. Let me just load that up. But most of it is based on sort of known procedures, and in some cases there's existing software. In some cases you have to reinvent the wheel,
Are
and
there
then
any good written material for this, like any PDF or books?
I mean, no, in a general sense, no. I mean, because a radio data reduction is incredibly different than an optical data reduction, um, and so it's really hard to have a resource that kind of universally covers how all these different things work. And so a lot of it is, yeah, I mean, there's individual documentation, but and there are, I mean, there are some resources out there for things like principles of radio calibration and imaging and stuff. So that that try to broadly cover all sort of standard radio telescope properties. There's some documents and some like summer school kind of training things. Um, I don't know about optical. There is presumably similar documentation out there,
I see.
but
So it's mostly like work
yeah,
with people and learn as you go. Okay.
yeah. I mean, so much of different aspects of this are bespoke. Essentially, they're customized for the specific data set in question, for the specific telescope, for the specific problem you're trying to solve. And so, in some sense, like when you start on a completely new project with completely new data, the first step tends to be, okay, what have other people done with this kind of data, with this kind of with this telescope, if that's been done before. Try and develop the same methodologies, and then once you've exhausted or you've gone as far as you can with sort of the common or the standard methods, you have to kind of, yeah, try to develop something as much as you can based on your knowledge of different techniques that can be used and stuff like that. And so there's a whole corner of astronomy research which is algorithm development and testing to take ideas from statistics and mathematics on how to deal with different kinds of information and test whether or not those can be useful on different kinds of astronomical data. And I've done a little bit of that work. But so yeah, I mean, so I pulled up this figure. This is a pipeline that I am currently working on for a very large survey, which will happen in the next 2 years. And so yeah, each of these blocks is a different step in the process, and it kind of goes on. Um, but essentially, each of these boxes is either using an existing program. Like, so for example, on the left side, a lot of this is all stuff that's being run by the observatory, and they have written their own software to do handling the imaging of the data, handling the calibration and stuff. And so each of these boxes is essentially its own little software tool to some degree, and each one can more or less be developed by knowing what the data looks like when it comes in and what we need to get out of that particular box in terms of how does the data need to change, what are the effects. And so it looks like it's a really huge problem, and it kind of is, but you can break it down into a lot of individual steps that are actually not that difficult to develop sometimes in terms of having a fairly logical flow to it. Like some of these steps, like ingest or transfer. This is a data storage system, this CASDA, and so this is essentially saying, okay, we need a piece of code that will identify the right files on some server and just download them. And so that doesn't have to be a complicated piece of code, right? Just to have a little script that downloads files. And so a lot of these are fairly easy things. And so once you break it down, it becomes tractable. I mean, some of the stuff is a lot more complicated. Like particularly some of the stuff near the bottom here. This is stuff that I've had to develop, and it's kind of stuff that maybe someone has not done before, and so I have to try different things to see what works. But yeah, it's really hard to talk in generalities, just because so much of this is really, really customized for the problem. Yeah, but good questions, I guess. Any other questions, I guess, before I move on to something new? Because I think I've kind of gone through most of the web resources now.
So like, what's the for the okay? I asked that question. Like, what's the general language which you use?
Yeah, so that's something I was actually planning to get to. I can jump that forward a little bit, which is programming wise, I do 90% of my work in Python these days. 95, probably more like.
Even
Um,
the pipeline which you are talking about right now.
yep.
Okay, could you?
Yeah. I mean, so most of the pipelines have been series of Python scripts or Python components. I mean, and plus some fraction of larger packages, particularly for things like the observatory tasks, like calibration, where it is much more complicated software and much larger data sets. That tends to be packages that other people have developed, and I think most of them are in C. It's for the really big packages. Um, but once you get to sort of the very custom specific stuff, it's the standard in astronomy is to do it in Python typically, because Python is very easy to do trial and error, to build things and then sort of check the results to see if they make sense and if it's working as intended. And so it's Python is very nice for sort of rapid iteration and prototyping, and that is to some degree the biggest part of what writing a lot of this astronomical code ends up being. Is particularly when you're working on individual projects, you write code to solve one problem one time. And so you don't necessarily need it to run fast, because 99% of the time spent is writing the code and not running it. And so we're not really worried about the efficiency that you get out of, say, C, versus the ease of design, which Python is really good at.
I see.
Um,
Also, you work on the front end data reduction, like where the data is coming from the telescope real time and you are processing it.
no, not really. So that tends to be handled by the observatories. Um, and so what is typically done is, yeah, the observatory will have its own systems in place to handle data in real time, and then what's traditionally done. Let me see if I can even find some interesting examples here. Oops, I can't spell. But so what's traditionally done by most observatories, such as, for example, the VLA here, is they will archive a very sort of basic version of the data, um, which has no calibration. It's simply the data saved, I guess, directly off the telescope with as minimal processing as is possible given how the telescope is set up. And so, oh, I'm trying to remember. I had a VLA project years ago, and I don't remember the name of it. Yeah, so I won't be able to search anything very easily. Can I remember what year that was? That'd have been 2008. Well, I mean, maybe the details here aren't matter, but essentially, what would be returned by an archive like this is a uncalibrated, and in the case of radio data here, an unimaged data set, so just pure visibilities. Um, and then it's up to the scientists who requested the data to essentially handle everything after that in when they have time as they can, and so it can take months to years to get data sets processed.
Yeah, so
These
why
days,
they
what tends to
why they don't
sorry.
have a pipeline setup like which will process the data real time? Because like because this is all redundant work because many observatories like give the processed data, isn't it?
Now, so there is a transition now to sort of standardizing the processing, and I think part of the reason it wasn't done before is it simply was less standardized as to how you calibrated and processed the data. There was more variations, and particularly a lot of variations in how people set up their observations in terms of how the data was what data products were being stored, and so it was harder to come up with pipelines that could handle all of the possible configurations of the telescope, I guess I would say. Um, and so, but more recently, observatories now also have more budget for computing power, which has helped. But there has been a push to more sort of standardized versions of how things are processed. There's been a lot of algorithm development on how to handle problems in the data in smooth ways so that they don't crash things out. Um, and there's also just a shift in what people expect. And so, particularly as data sets have become more complicated, it's become more annoying for every individual astronomer to have to learn how to handle and calibrate all of these data sets. And so it's become more efficient for a handful of people to know how the calibration works and to deal with that at the observatory, and then hand over calibrated data to the scientists to work on. And so there has been that trend now. And so, like for the pipeline I'm working on now, the big massive flowchart I just showed, most of the first box is all handled by the observatory, using software packages that they have developed with their own software developers there. Although we have had to contribute uh, some ideas and take part in testing, I guess, because the observatory doesn't have enough people, particularly enough specialists who know here's what the end result has to look like and here's how we assess whether the end result is good enough or as good as it can be, kind of a thing. And so there is this sort of constant connection between the observatory and the astronomers who are using the data to try to optimize things. And so yeah, it's a process.
Okay, so that brings me to another question. Like like the way you process the data might bring in some caveats, right?
Mhm.
It might make a observation more dominant than the other. Like how does one consider that and take all of these factors?
I'm not quite sure I understand the question, I'm afraid.
Like are there anything like the way the data is processed that it might morph the data itself like in such a way like we are forcing something which shouldn't be there, like we don't
Yeah.
expect it to see but the way we have processed it it's coming up, and why we might be missing other details which we didn't expect, so our pipeline isn't designed to capture that.
Yeah, yeah, that's a big problem, and that is one of the arguments against too much automation. I guess is that if people aren't looking at the data carefully, they can miss problems like that. And there have been problems identified. For example, in radio astronomy, there's an algorithm called self calibration, which can go horribly wrong if there are biases in how the algorithm has been set up. I had a friend of mine who was doing a training camp, and he was able to demonstrate how this self calibration algorithm can go horribly wrong. I mean, he did have to set the like tune the algorithm so that its settings were really unreasonable. But he managed to basically make a radio image that looked like a smiley face, as an example of if you do things wrong, things can go wrong. And the solution to that broadly is to make sure that all of the methods that we're using are carefully tested so that we do know what the valid limits are. And so the goal is that we're generally only applying methods that we know don't cause problems to the data, within reason, and that we're not pushing the methods too far. And so there is this whole process then of sort of trying to check things at every stage as much as possible.
Okay.
But yeah, there are some contentious issues there in the sense that some people don't necessarily want to spend a lot of time back checking their data because it does take time and there's a lot of work to do.
And you also
Whereas
need the required skills to do that.
uh, and that's hard to quantify again in a general sense. Is it's something I think that develops a little bit with experience in the sense that people have to spend time working with the data, spend time understanding the algorithms that they're applying, and I guess to some degree, yeah, it's sort of experiencing different data sets and how they behave, and seeing what can cause things to go wrong, and so it's really hard to generalize. And so I think that's also been a major challenge for the development of software pipelines. Is how do you write a software pipeline that can anticipate everything that can go wrong? And so I think a fair part of, not a large part of my job, but definitely a part and part of other people's jobs is to check, when we're running a pipeline, to check the outputs and say, okay, this is weird. Where, go backwards through the process to see, okay, where did things go wrong and why? And so it's a bit of a debugging process to a degree. But the annoying part is that quite often the pipelines will run, seemingly fine, and it's only when a human inspects the outputs that you can tell something is wrong.
So this is like a common problem which you have among different surveys and data.
Yeah, I think it is a common. I think, yeah, to some degree, there is a universal problem that in order to best judge the data, you need to be an expert in the data. And how do you become an expert in the data? By spending time with the data, and so it's a bit circular in the sense that, yeah, you there is no clean path, I guess, uh, to being able to sort of solve it cleanly in terms of I guess no method that you can say, if we follow this procedure, we will definitely come out with good results and everything will work. So it's a dirty process. Yeah. All right. Let me see. What else did I have that I wanted to show off to you guys? Fitzviewers, actually. So I'm not sure how much you guys have been playing with Fitz files. So Fitz is the default format for most astronomical data and has been for like 30 years now. And so if I know there's been some people on the server who've been trying to play with, like, I guess, Hubble data and other kinds of data that you can get from various archives. And so there are different ways of interacting with these FITS files. The basic version of a FITS file is that it's a file with image data in it. And so there's a couple of different image viewers. This is one that's free. This is something called SAO DS9, which can be found pretty straightforward on Google, and it's a basic FITS data viewer that can run on, I think, any platform. And I'll confess, I don't use it that much, but the one that I do use is from the 90s, and it's a bit fussy, and so I don't really want to recommend it to anyone. But this is
What's
one
its
that's
called?
very. So the
What's
one that I use is called KViz, Karma Visualizer. But it's a bit finicky, and it's not maintained. It's old, and so I can't in good conscience recommend it. But this is one that's a little bit more user friendly, but it's I just find it a little less easy to use personally, because I've gotten used to using KViz. But yeah, it's sort of easy to. How do I zoom out in this? See, so this is the problem is I don't use this enough, so I'm trying to figure out where are the buttons that I need here. But yeah, you can load up image data like this and sort of look around and explore the data a little bit. This and sort of different. I mean, any Fitzviewer has the option to adjust image scaling so that you can bring out different levels of detail here. And so if you get the details just right, and then some of this nebulosity starts to come out. So this for example, try and blow this up a little bit. This is an ionized region, an H2 region in the galactic plane that's quite large. And the reason I gravitated to this one is I analyzed some data which showed that this particular ionized region casts a really interesting shadow in radio polarization. But yeah, this is a radio map of the galactic plane.
Like shadow in what sense? Like, is it really the shadow which we are familiar with, or something different?
Well, you're not seeing the shadow in this picture. So this is not a polarization picture. This is just a radio brightness image. But when I say a shadow, in the case that if we look in polarization, and I don't have that data on this computer, but sadly, but if you look at this part of the sky in radio polarization, there's background emission kind of throughout from more distant parts of the galaxy. But if we look in the direction of this particular ionized cloud, it's dark in polarization. There's less emission in the direction here than there is around it, and that's because the emission is from further behind, and this H2 region, this cloud, is blocking the emission from behind, the polarized emission, radio emission. And so we see a dark region because we are sitting. Basically, the galaxy is bright, and this object is a shadow blocking it from reaching us. And I quite enjoy it. When I found it, it's like, yeah, that is cool because we are sitting in the shadow of this particular thing in some sense. But yeah, so if you ever find image data that you're interested in, something like this is an easy way to load it up. This is a very lightweight Fitzviewer. If you want to do something a little bit more involved, the one that I use, well, I'm starting to use because it's currently being developed, and so it should be very good once it's come out, is a new software called Carta, which is being developed by a team in South Africa. And so this is actually not the newest one. I think Carta 3 might have come out by now. I just haven't downloaded the newest one yet. But let me find the same data file. So this one has a slightly more modern and sophisticated GUI. But there we go. Yeah. And so I personally find this a lot easier to use. So if someone is going to spend a lot of time looking at Fitz data files, this Carta program is quite sophisticated and quite nice. It's got a lot of different options if you want to try, like for example, you can do color scales, classic grayscale, different options depending on what visually appeals to you. But yeah, this offers quite a bit of interesting functionality, including one of the really things that's very important in my work for using Carta is it handles 3 and 4 dimensional data sets fairly well. And so let me find an example of that. Should have some examples. So it's 4. I haven't looked at this data in a while. Hopefully it's pretty data. It's not the prettiest of data, but but so this is a data cube where it's got different radio channels. And so at different channels, its behavior of the data is changing. essentially. And so what's really nice about Carta is it has some really powerful built-in tools for essentially plotting, exploring the data in 3D. And so this is, I'm seeing a single image here, but then I can also see the whole spectrum where I'm sort of looking through the third axis at one location at a time. And so I can then sort of use this and mouse around to explore, where the data is behaving in an interesting way. So, here we're
What
seeing some
object
kind of
is
a
this?
sinusoidal oscillation.
Like, what object is this?
This is probably a patch of empty sky. So I think we're probably seeing diffuse radio emission from the Milky Way. Probably. So not a sort of well-defined compact radio source of any kind. Let me see if I have anything that's a little bit prettier to show off here. Not sure that I do. Yeah, I don't know. I don't have a lot of pretty data sets on hand. Actually, this one might not be bad. This is a simulated data set that I made. So I simulated it to make it look like it has a very nice source in the middle here. And so, yeah, I mean, this is a very simple simulation. There's a chunk of empty sky, and then there's a source here which has a spectrum that's just mildly noisy, basically. It's mostly flat with some noise on it. So it's not the most interesting radio source. But yeah, it's just a simple simulation that I generated to test some software. But I can sort of explore the data very quickly and determine its properties using something like this. And so whenever I get a new data set, I want to check it, I would load it up in Carta or in something similar to look around and to see what is present in the data, see what kind of interesting features it has, how it's behaving, et cetera, et cetera. Yeah. So let's see. So that's data viewing. Let's see. What else do I have that I'd like to show off? I guess maybe let's talk a little bit more about the programming side, because I think that'll be interesting, I guess, a bit more for you guys.
Yeah, yeah.
So yeah, so I mentioned Python before. So I kind of have two different computing environments that I like to work in, or two sort of tools, I guess. The first of which is Jupyter Notebooks, which I really love because they give a really nice tool for sort of trial and error, just trying things out and seeing the results really quickly. So do I have yeah, here's an easy one actually. I think this is like a little simulation that I did. And so yeah, so the nice thing about Jupyter Notebooks is you can add some formatting like headers and stuff. And then basically rather than having one very long program, you break things up into sort of smaller cells. Let's actually start running some of this. This should be able to, hopefully this code still runs. I've changed some things since then, but so yeah, you can set up some like variables in different ways, and then you can go back and edit them and rerun just that block of code very quickly if you want. And then generate a plot, check the plot. If you don't like the plot, you can go in and change the data. Let me actually change these back to something else like this. I change the data and check that it's what I like. Yeah, so I'm not going to go through all the details of what exactly this is doing because I don't think it's super interesting. But I'm essentially running some code that I developed elsewhere, imported it, and running some of the functions to test to see basically what kind of results come out. And so what I really like about this as an environment is simply the ability to try things. And so, like, for example, what if I want to tweak this plot? Maybe I want to zoom in a little bit on just the center. And so it's super easy to just say, all right, let's change this little, one line of code that sets the limits of the plot, rerun it, and boom, I now have a new plot. And it only took me 10 seconds. I don't have to rerun an entire program, including, for example, if some of these earlier calculations are, maybe they take a little while, maybe they take a couple of minutes to run, depending on what I'm doing. But if all I want to do is adjust the plot, I don't want to have to rerun it for 5 minutes every time. That's just not efficient. And so being able to break it into little chunks and iterate and try things really quickly has been it's a very satisfying environment for sort of trial and error. And if I'm exploring a data set, for example, I want to load in some data and I don't know how it's going to behave. I just want to try some different things. This is an environment that makes it super easy. Or if I want to make something that I want to share with someone. Let me try and find a good example of this. Actually, I think I have one. Is it this one? Maybe. My naming scheme is not the best. That's something I need to develop, get better
But
at.
that's certainly interesting. I was about to say.
But yeah, so this is a Jupyter notebook that I made partially as some data exploration, but I also intended the notebook itself to be kind of like a report that I could share with my colleagues about what I had done and what I'd found. Right. And so I've like wrote like a little paragraph or 2 paragraphs of what it is that I'm trying to do. And then I'm setting up the code. And so if I share this with my colleagues, they can immediately go through it. And I didn't comment the code properly. So, again, not a great example of good style, but in principle, people can see what I did, and I have some discussion about the results here, and so people can look at the plot, look at the discussion, see if they agree with it. Maybe if people want, they can modify some of the code and see how that changes the results if they want. So yeah, results section. So it's like a little lab report almost, in the sense that it combines code. Apparently, some of this code doesn't work because I've got a debug trace here, um, but yeah, and then I'm running sort of different simulation experiments here, and we're talking about the results. And so it's really like a lab report kind of a thing in a code environment. And so including the ability to typeset equations and things, and so I can discuss results, and then yeah, and this is a case where a colleague of mine asked a question in response to some of the results that I showed. Just add a section to the notebook and generate some new plots and stuff. So this is a very nice environment for that kind of iterative, explorative kind of thing. The other one that I tend to use is when I sit down and I need to actually write some more serious program, a program that I want to run in a sort of standalone environment or as a command line tool. And so for that, I have sort of a more proper, typical developer environment, which is currently loading up. Give it a sec. Once it's loaded in, I can drag it to the other monitor again. Oh, my poor laptop.
I think you should close some of the things.
Probably. Okay. No, it's just this is weirdly heavy. It is loading in. Yeah. Okay. So it is loading up, and so this is your much more typical classic developer environment in the sense of having files, with hundreds of lines of code in them. Still loading. There we go. And so I use this when I'm writing code that is longer that I want to be easier to rerun, or if I want to run it, as sort of a standard Python module that I can import into other environments. And so, there's many different developer environments available. This is Spider, which it came with the Anaconda Python install, so it's not like I've experimented with different ones and decided that this is the one I like. It's just the first one I tried and it works. And yeah, it's also kind of nice in the sense that it gives you, you have a built-in Python interpreter that you can just try lines of code or sections of code on and see if they're working as you expect them to. And then you can, yeah, basically go through. So this now is actually a section of one of my pipelines, which I'm not going to get into what the code does exactly because it's not that interesting. But it's got a whole series of functions and import statements and related codes and things like that. Like classes and all the good programming things that proper programmers do. This is the kind of environment when I have that kind of work, I guess. So what else is there to say? And so yeah, I guess something that is maybe overlooked as an astronomical software, but is really important, is just the standard Unix shell interface. And so being able to do stuff on the command line is a super useful skill to have as an astronomer or someone interested in doing astronomical stuff, because there are a lot of things that are really easy to do in this kind of an environment. Let me see if I can find some examples here of things that I like to do.
And the funny thing is that for the optical regime, image detection and all, there is a whole
Mhm.
IREF thing which only runs on the in the command line, and
Yeah,
it's
yeah.
really hard for
IRAF is, yeah.
the old astronomers to move on.
Yeah. IRAF is slowly dying because it's hard to run on modern systems and it's hard to use. Radio astronomy had a similar package called APES for a lot of years, and APES has finally died, and it's been replaced by new software that has GUIs and has other kind of useful modern conveniences, I guess. But yeah, not everything has a nice GUI, and not everything is worth the effort of developing a GUI for. For example, so one of the things that I actually, let's go to a different example here. What's a good example? Probably no, not that one. Sorry. Nope, not that one either. Yeah, that's probably an easier one. And so, like for example, one of the software packages I maintain has a series of command line tools for polarization analysis, and so this is a Python module that I half inherited and then wrote the other half. And it does some particular aspects of radio polarization analysis that are quite useful, and so it's quite popular with the small number of astronomers that need to do that kind of a thing. But it's not necessarily worth having a complicated GUI or anything that I would have to maintain the software for. And so being able to work in this kind of command line environment, yeah. And so now this code has spat out some plots. But I mean that's basically the level of what this code does. I mean, so the underneath is a couple thousand lines of Python code. It's done some analysis on some data, spat out some results, but it doesn't need to be anything more sophisticated than that. And so yeah, I used to do a lot of scripting actually within the sort of the bash shell command line environment, because it was during my PhD I was working with some observatory software that would operate on images, and maybe I had a couple hundred images, and so I'd write little bash scripts to sort of for loop over every image in the command line and run it. And so stuff like that, being able to do that kind of thing quickly and easily is a super handy skill to develop, I guess. People interested in working with data or working with simulations even. And so that's, yeah. As well as, yeah, related things like just like being able to log into remote systems and check on them. So right now I'm logging into a virtual machine running on a supercomputer in Victoria, Canada, where I have some jobs that are running. Okay, it looks, so it says 100%, but it is still running because the progress bars are not set up quite properly. And that's my fault. But yeah, so this is a,
Is this a like you are running the code on a supercomputer?
yeah. Well,
Okay.
it's on a virtual machine set up in a supercomputer. So the virtual machine is not that powerful. But
So is this written in Python?
yeah, the pipeline that I'm running right now is, yeah.
Okay.
And yeah, it's fine. So yeah, this is like right now. Let me see what's it doing. I can probably check the outputs actually. Okay, yeah. So it's actually just about done because it's starting to produce output files. And so this particular pipeline is taking in. Let's see. So, oops. Let's flip this around. Yeah. So there. Yeah. So I have three data files here that are each 64 gigabytes. So I'm taking in 3 times 64 gigabytes worth of data. I'm doing some radio polarization processing on it. Um, and so far it's output. Yeah, it's output some of the data. I'm outputting some 46 gigabyte product. I'm outputting some 23 gigabyte product, as well as some half gigabyte data cubes. Can I load up one of these actually? I don't know if I can load one of these up in real time, but we can try it. But yeah, and so as part of my work, I'm just comfortable. I've gotten familiar with how to access these kinds of systems remotely and how to work on them, how to set up computing jobs and check the results. And so this is loading in. Let's see how long it takes to load half a gigabyte of data from. I mean,
Is
thankfully,
this
it's not
which
streaming any.
you were talking about?
Yeah, yeah. This is the KViz Fitzviewer. So it's it's old. It was last
But
developed in
it's
the
good because
1990s.
it's installed on that system, right? You can't just literally a
I
60.
had to install it on the system. So the
Oh,
nice thing about KViz and Karma is that it is built around command line, and so it is very easy. Well, no, it's not actually easy. It's a pain in the ass to install, but it is possible to install it on a remote system like this without any kind of GUI interface or anything. And so it's going to take us, yeah, it's going to take a minute, but it should load up the data. And then I'll be able to check whether or not the pipeline is running properly, which it should be because I spent most of November hammering out bugs in this particular section of the code. All right, okay, yeah, it's loaded up. And so yeah, okay, that's roughly what I expect it to look like. Which, I mean, this is not ideal data, but yeah, there are radio sources. All kinds of radio sources and a lot of art. Yeah, so this is data that has a lot of artifacts just because of limitations in our processing ability / algorithms and stuff. And so yeah, like these sources, this is probably one fairly bright radio source, and it's got all these artifacts around it because of, well, basically because this data is a bit messy and complicated, and dealing with
yeah,
it
that's what
properly would.
I was asking about. Like the way it's processed, it shows these artifacts, right? It looks like ripples, and I don't know. Like you are a astronomer, so you can figure it out. Like it's the caveats and all. But I, as a like a amateur or newbie, can't even know like if it's a real thing or not.
Yeah, yeah, it's tough, and I don't know that there is a good solution to it. It's the kind of thing that you. I mean, and I have this with students as well that I work with. Is you just kind of have to throw data at people, and eventually you start to get the hang of it. I think, in the sense that you learn what kind of things to look for to give you clues about what's real and what isn't, and you learn different failure modes, things that can go wrong. Um, Things like that. Do I have the? No, I don't have the total intensity image for this data. Or do I? No, I don't. But yeah, yeah. I mean, data is messy. There's just no way around that. I think it's the nature of it. Is we are pushing the limits of what the telescope can do. What we have limits of what we have software to be able to do. Limits of a computing capacity, and so yeah, it's messy because the things that aren't messy have basically already been looked at, I guess, or been done.
Also, what telescope was this?
So this was Ascap, the Australian Square Kilometer Array Pathfinder. And so, shoot, I pressed the quit button. I don't know. It would have been interesting to show it off some details of it. But so the neat thing about Ascap, hopefully this won't crash super quickly. But so you see the sort of those series of circles here around the perimeter. So Ascap is weird by radio telescope standards in the sense that most radio telescopes have a single circular beam in terms of the area of sky that they image. Ascap has 36 beams simultaneously in kind of a packed grid. And so the middle regions are actually a superposition of multiple beams that are processed simultaneously by the telescope. And then mosaic together into one thing. But at the edges, where you only have the outermost beam, you essentially see the circular pattern for it.
Also, I don't know like if you can see that or not, but the outer rims look brighter than the middle one.
Yes, so they are noisier. So one of the properties of radio data is that the beam becomes less sensitive as you go to the edges, and so if you had the same brightness source at the edge of the beam, it would look fainter, and so we have to correct for that as calibration. And so it's essentially division by a number less than 1. We know the sensitivity, so at the edge maybe the sensitivity is 30%. So we divide by 0.3, and so the actual brightness goes back to the true value, but it also drags up the noise. And so the noise would become 3 times higher at the same
Okay,
time.
so
And
it's
so
a
that's
SNR issue. Like signal to
yeah.
noise isn't that great over here. Okay.
Yeah,
And the
yeah. So
mosaic thing which you
basically,
talked about, that makes thing even more complicated. Like we have like the brightness of an object is like let's say it's overlapped by three different sections. So it will
mhm.
become three times, isn't it?
No. So the mosaicing software knows it knows how to renormalize essentially. so that
Okay.
so that the brightnesses are conserved properly. Um, but okay, so I see. Yeah, Safe Practice asked about the software. Um, so this particular Fitzviewer is from the 90s, and it still works more or less. It doesn't have all the new features. There are some new data sets that just crash out on it. But it still works for basic things, and so there are newer Fitzviewers. I demoed them a bit earlier on, uh, and so some of them are still in development and are getting new features, and some of them are stable. But basically, in some cases, the old tools are good enough, and then if that's what you're used to, then it's fine. And so you also asked about machine learning. Uh, I think there's a tendency to use machine learning as ask whether it can solve everything. And I mean, yeah, there are tricks you can do, but I think the danger with machine learning is it's hard to be confident that you understand exactly what it's doing to the data. And so usually with these kinds of processes, you want to be able to say, I know exactly what's happened to the data as much as possible so that I can trust that it hasn't changed the source position, it hasn't changed the source brightness, it hasn't changed the source size, it hasn't changed anything that might be scientifically interesting. And so you have to be kind of a little bit cautious, I think. And this has crashed. There we go. Let's see if that saves it. But probably trying to do too much on this remote machine at the same time. Whatever. This is on the remote VM, so I can let it sort out its own crash. I can just disconnect.
I hope that's not concerning, right?
It shouldn't be a problem. It shouldn't mess up the pipeline. And even if it does, the pipeline's been running for... Okay, there we go. Disconnected. So the pipeline only took 3 days to run on that particular data set, so I'll just start it up again and it'll run again for 3 more days if it needs to. Yeah, I don't know. What else can I show? Anything else you want to see?
Probably some like Atlas tools like Aladdin and all. Like
Yeah,
I started
Aladdin's.
using Aladdin, and but it's like quite slow and all.
Yeah, it can be. I mean, it's. Oh, have I spelled this wrong? Is it? Pretty sure. Oh yeah, it's 1D. That's why I did it wrong. Okay. All right, load up. Yeah, I do use. Oh yeah. So I installed the newest version of Aladdin yesterday because I had a feeling it would come up, and Mac OS does not like it. Give me a second. Mac OS security has gotten very fussy. So yeah, I guess that's its own conversation as well. So yeah, Macs tend to be somewhat common in astronomy research because they have access to the Unix shell, the command line environment, and so
Also,
all
you
sort
can
of
get away with
Unix
Linux
compatible.
as well. Like that's what I use.
Yeah, you generally can, and that works fine these days. There's a lot of inertia in the sense of supervisors just buying Macs for their students, I guess, because that's what they use. Um, that's what got me into Macs, I guess, is my supervisor bought me one. And it's like, all right. And then 10 years later, it's like, well, all of my files are on Mac, and in sort of Mac, some of my software is Mac only, so I guess I'm stuck now. They've trapped me.
And economy also come
But,
into play over here. Because
yeah, that's
in
understandable.
India, most people use like Linux.
Yeah, that's quite sensible. Um, all right. So yeah. So Aladdin is a really nice tool for visualizing data, and its most powerful thing is its access uh, to various online catalog and databases, essentially image databases, and so it is loading slowly. Is there anything I can quit? Let's say I don't need this one. Uh, Most of the stuff I probably don't need that one. Actually, yeah, that's just the paper. We don't need that anymore. Quit out. Now let's give this a second. Streaming it is also, yeah. My Mac does not have a graphics card, and so streaming things is it's going to put some burden. There we go. So yeah, so in principle, yeah, you can pick an area of sky around something you are interested in, and it'll take you to the right chunk of the sky. And by default, it loads up the optical image. And so here we are back to my second favorite galaxy, NGC 7331, which is a nice pretty spiral with a lot of neighboring
Are you
galaxies as
like,
well.
is the screen changing right now? Because it's static for me.
Uh, okay, interesting. Yeah, not sure. Let me check this. I'm going to turn off my camera just to save compute resources. Yeah, give me a
Are you
sec here
able
to
to
try.
see the changes safe practice? If you can confirm.
Yeah, okay. So I guess are you seeing a galaxy now or not? Just to check.
I'm not able to see anything. Like
Okay.
I'm just seeing the Aladdin load screen.
Yeah. So it's I mean it's also possible that it doesn't play well with streaming. Because it is,
Just
I don't
close
know.
that. Then I'll
Yeah.
send the
I guess,
link in whiteboard.
yeah. I mean the short version is that Aladdin is really nice for being able to load up catalog data and sort of image database data and be able to look at different, whatever area of sky is interesting and look at different data sets that cover that part of the sky. You can compare the optical and yeah, it's good practice. Good idea. Why don't I stop the stream and restart it and see if that fixes anything? Okay, so that's that. Screen 2. So it should take a second to come back up. So yeah, I guess let me know if you can see anything / when you can see anything. I can try and free up a little bit more RAM if that'll
It's
help.
loading on my side.
Hello?
Hello, can you hear me?